So good morning to Ananda. Good morning. So please kindly confirm audio, video and screen once. Please kindly confirm the audio, video and screen. Is it clear? Okay, fine. See, let's look at this question in the classroom objectives, classroom practice questions. Go through this. Yeah. See, the series impedance of a three-phase transmission line, is 0.05 plus J 0.35 ohms per phase per kilometer. Okay. So I can write simply Z is equals to series impedance 0.05 plus J 0.35 ohms per phase per kilometer. Okay. So if the spacing between the conductors, distance between the conductors and the radius of the conductors, means size of the conductors are doubled, then the series impedance per phase of the line will be. See, actually, series impedance of transmission line is nothing but R plus JX. R plus JX. R is the series resistance, we can say. X is a series inductive reactance. X is a series inductive reactance. And that X you can write it as 2 pi F into inductance. X you can write it as 2 pi F into inductance. And what is that inductance formula? 2 into 10 power minus 7 ln of GMD by GMR. 2 into 10 power minus 7 ln of GMD by GMR. Or else you write 0.2 ln of GMD by GMR millihenry by kilometers. Millihenry by kilometers. Like this you can see. Okay. Simple, very simple thing. See, spacing between the conductors doubled. See, if the distance between the conductors are doubled, definitely GMD value will be doubled. GMD value will be doubled. Next one. Radius of conductors are doubled. Then definitely GMR will be doubled. Okay. So spacing between conductors doubled, I can say. Spacing between conductors doubled means I can say GMD will be doubled. GMD doubled. Next, radius of conductors doubled. Radius of conductors doubled. Means I can say here GMR will be doubled. GMR will be doubled. Radius of conductors are doubled means I can say GMR will be doubled. So GMD by GMR, that will be remains constant now. GMD doubled, GMR doubled means this ratio will be remains constant. So inductance value will be remains constant. So X value will not change. X value is not going to be changed. Okay. What about resistance? Resistance is inversely proportional to area of cross section of conductor. Means resistance is inversely proportional to radius square. Radius square. So as a radius is getting doubled, definitely resistance value will be reduced by 4 times. Okay. So let me show. Let me show here. As R is inversely proportional to radius square, radius is doubled. So we can say a resistance value increased by 4 times. Sorry, reduced by 4 times. Resistance value reduced by 4 times. Reduced by 4 times. So obviously with this change, the new series impedance will be, resistance will be reduced by 4 times means it will come to be 0.05 by 4. Real part plus J. Imaginary part is 2 pi F into inductance value. Frequency no change. Inductance also no change because of this. So I can say it will be remain same at 0.35. So it will come to be 0.125 plus J 0.35 ohm per kilometers. Ohm per kilometers. So I think all of you getting this one? All of you getting this? So if radius of conductors and spacing between the conductors are doubled, then we don't have any change in the inductance of transmission line. No change in the inductance of transmission line. What will happen to capacitance of transmission line? What will happen to capacitance of transmission line because of this increment in the spacing between conductors and radius? Tell me please. What will happen to capacitance of line? That also not going to be affected. Capacitance of transmission line also remains same. So I can say because of this change what we have mentioned, there is no change in the values of L and C, but there is a change in the resistance value. Particularly that resistance value was going to be decreased by 4 times. Yeah. So let's take one more problem in this L and C calculations quickly. Let's see this question. Yeah, go through this. Yeah, see this. Two arrangements of conductors are proposed for a three-phase transmission line. Two arrangements of conductors are proposed for a three-phase transmission line. One with equilateral spacing of 4 meters. One with equilateral spacing of 4 meters. The first one, equilateral spacing of 4 meters between the conductors. Okay. And the other, a flat with 4 meters between the conductors. Second one is a flat with 4 meters between the conductors. I will show it how it is. As shown in the figure. The conductor diameter in each case is 2 centimeters. Means radius of conductor in each case is 1 centimeter, we can say. Okay. Next, assuming that the line is transposed in both cases, that's well and good. Which one of the following statements would be true? See, in this problem, he is asking us to compare the values of inductance and capacitance. The values of inductance and capacitance from system 1 to system 2. From system 1 to system 2, L and C values we have to compare. See, already we know that these L and C values are depends upon the GMD and GMR. GMD and radius of the conductors. Anyhow, radius of conductors are equal in both cases. Na? Radius of the conductors are equal in both cases. So you don't get any change in the value of GMR. But because of this configuration, there may be a change in the value of GMD that we have to check. What is the change in the GMD? According to that, how is the change in the inductance and capacitance value from system 1 to system 2? Okay, so let's say in the solution, first one I am taking up. It is given as an equilateral spacing. See, this is not a bundle conductor. That's a thing what you have to be very clear now. It's not a bundle conductor. It's not a bundle conductor. It's two three-phase systems what they have given. Two three-phase systems they have given in the question. Okay, so radius of each wire is 1 centimeter. Radius of each wire is 1 centimeter. You call it a phase A conductor, phase B conductor, phase C conductor. And distance between these two conductors is at 4 meters. Between these two, again 4 meters you can say. Between these two, again you will have 4 meters. Distance between the conductors is 4 meters. Okay, simple, very simple thing. What is GMD of this system? You call it is GMD1. GMD of this system is cube root of 4 into 4 into 4. This number will be 4 meters. And GMR of this system is R dash. R dash means 0.7788 into radius. Like this you can call. And let's take second system here itself. Let's take second system. Second three-phase system it is. Transposed already we have discussed now. Yeah. Let us see this flat spacing system what we have. This one. So I'm showing like this. 1 minute, please. It's a flat spacing three-phase system. Again, I'm saying you it's a different three-phase system. It's a different three-phase system, and you can call this is a phase A conductor, phase B conductor, and phase C conductor. And distances between the conductors is at 4 meters. The meaning of that is this distance will be 4 meters, A to B, and then B to C gap is also 4 meters. That's the meaning here. All of you getting this point? All of you getting this point? And radius of each wire is obviously 1 centimeter, what he has mentioned. Radius of conductors is 1 centimeters. Yeah, please complete it, Tanmay. Tanmay, I will show that slide what you have asked me. I'll show it later. Just please complete it first. Okay. See, what is GMD of this system? Already he said it is transposed, right? Already he said it is transposed. After doing transposition only, we know we can write GMD as cube root of DAB, DBC, DCA. Okay, so you can write this like 4 into 4 into 8. So under cube root. So cube root of 4 into 4 into 8. What you are going to get this one? What you are going to get this one? Tell me please. Sir, if they gave 4 centimeters, then it's a bundle. It's not bundle conductor, dear Imtiaz. They said these are two different systems, right? And why you are saying it's a bundle conductor? You should not say that as bundle conductor. You should not get the type of question based on those distances. 5.04 meters. This number is 5.04 meters. What is GMR2? GMR2. So it is 0.7788 into radius. Radius is 1 centimeter. Like this you can see. Now you can say GMD1 is less compared to GMD2. GMR1, GMR2 are equal. Let me write in the next slide quickly. From this comparison, we can confirm that GMD of system 1 and GMD of system 2 are equal. Sorry, less than. GMD of system 1 is less compared to GMD of system 2. GMR of system 1 will be equals to GMR of the system 2. Okay, now you tell me please. If GMD is low, how is the inductance value? If GMD is low, how is the inductance value? Definitely low. If GMD is low, inductance value will be low. See, for example, you can say here in this case, inductance is L1, capacitance is CN1. And here the inductance is L2, capacitance is CN2. So L1 will be less compared to L2. That's one comment what you can make. L1 is less compared to L2. Next one, CN1, it is greater compared to CN2. Because if GMD is low, capacitance is more. Just to go through with the formula. 2 pi epsilon naught epsilon r by ln of GMD by R. Yesterday only we have discussed about it. Okay, so capacitance will be greater if the GMD value was less. Okay, so CN1 greater than CN2, L1 less than L2. Which option is suitable one here? Option B. Option B is a suitable one to be selected. CN1 greater than CN2 and L1 less than L2. Correct option will be B. Answer will be B. Okay, quick. Let's extend this problem quickly. Sir, where will be the neutral located in the case 2? Sajan Singh, you will get a delta connected capacitors, right? The delta you have to convert into star, and there the neutral will be located. Okay. So electrical equivalent you have to think, Sajan. Electrical equivalent you have to think. Okay, let's extend this problem a little bit. Let's extend this one. For example, if you compare the surge impedances, ZC1, ZC2, let me call ZC1 root of L1 by CN1. ZC2, you can say root of L2 by CN2. Like this. Root of L1 by CN1, and here you have root of L2 by CN2. Simple. Inductance is less, L1 is low, capacitance CN1 is high. Inductance L1 is low, capacitance CN1 is high. And how this change happens to ZC1 now? Inductance L1 is low, means ZC1 will be low. Capacitance CN1 is high, means denominator is more. Again, the value will be less only. So I can say surge impedance of equilateral spacing system will be less compared to flat spacing. Surge impedance of equilateral spacing will be less compared to flat spacing. ZC1 will be less compared to ZC. So let's compare surge impedance loadings. SIL values. SIL1, it is voltage square by ZC1, and SIL2, voltage square by ZC2. Voltage square by ZC2. And you know this ZC1 value was less, ZC1 will be less, so SIL1 will be higher. So surge impedance loading of system 1 is greater compared to system 2. SIL1 will be greater compared to SIL2. Surge impedance loading of system 1 is greater compared to surge impedance loading of the system 2. Clear? Next, let's compare maximum power transfer capacity also. Maximum power transfer capacity. Make it quick, please. So this is a problem in which we are comparing all the things of equilateral spacing with a flat spacing with same distances. 4 meters is a gap. 4 meters is a gap. Same radius of the conductors. Then only this comparison will have some meaning. Else you can say sometimes both the systems are having same voltage and current ratings. We have designed one equilateral spacing and one flat spacing with the same voltage rating and the current ratings, and then we are making all these comparisons. So you can say voltage rating and current ratings of both the systems are one and same. Then only this comparison will have some meaning. Okay, so let's continue with this. Maximum power transfer capacity I am writing. Maximum power transfer capacity. P maximum 1. Formula will be like mod Vs into mod Vr by X1. X1 that is nothing but 2 pi F into inductance L1. And maximum power transfer capacity in the second case will be like Vs into Vr by X2, reactance in second case. So it was 2 pi F into L2. Already we said L1 is less compared to L2. So Pmax 1 will be greater. So maximum power transfer capacity in the case 1 will be high compared to maximum power transfer capacity in the case 2. Maximum power transfer capacity in the case 1 will be high compared to maximum power transfer capacity in the case 2. SIL means surge impedance loading. Okay, so I want to make this comparison also. Kindly answer this one. Among these two systems, equilateral spacing and flat spacing, which system among these two will have more corona? Which system will have more corona? Is it a equilateral spacing system or flat spacing system? Which system will have more corona? Tell me please. Which system will have more corona? See, actually, corona depends upon two things. One is a radius of the conductors. Next one is a GMD. GMD is also one of the factors which will decide the corona, right? Already in the previous class, in the discussion of the bundle conductors, we said that to have low electric field intensity, GMD must be high. If the GMD value was high, electric field intensity is low, corona will be less. If you want to check back the equation what we have discussed earlier. See, among these two systems, system 1 is having low GMD, system 2 is having high GMD. So as a flat spacing have more GMD value, field intensity is less, corona will be less compared to its equilateral spacing. Okay, so I can write now as GMD1 less compared to GMD2, GMD2, equilateral spacing have more corona compared to flat spacing. Compare it to the flat spacing. Okay, so else you can say flat system will have less corona. Flat system will have less corona. So and let's take this extra flat spacing a little bit. A small extension I want to make now for the flat spacing. Just look here. For example, I have a flat spacing conductors here. Flat spacing conductors, something like this. Just I'll say it's a outer conductor 1, middle conductor number 2, next outer conductor 3. Call it simply phase A, phase B, phase C also. 1, 2, 3. Outer conductors 1 and 3, middle conductor is 2. You know these distances already. 1, 2 to 4 meters we have taken gap. 2 to 3, 4 meters. Kindly listen. In the previous case, means this one, we compared the equilateral spacing with the flat. Equilateral spacing and flat we have compared in the previous case. But in the present case, what I am asking is within the flat system. Within the flat system, among these 3 conductors, 1, 2, 3, which conductor will have more corona? Which conductor will have less corona? Which conductor will have more corona? Which conductor will have less corona? Tell me please, among these 3. What is GMD of the first position? What is GMD of the first position? First position will be root of 4 into 8. Root of 4 into 8. What is GMD of second position? Root of 4 into 4. Root of 4 into 4. What is GMD of the third position? Root of 4 into 8. See, observe now, this middle conductor is having lowest GMD compared to the outer conductors. Middle conductor will have lowest GMD compared to the outer conductors. So this middle conductor will experience more corona compared to the outer conductors in this case. Yes or no? So the middle conductor experiences highest corona or high corona compared with outer conductors. Compared with outer conductors. Compared with the outer conductors, we can say the middle conductor is going to experience the high corona. Okay. Yeah. So this is end of almost this line constants calculation. We left with only one small topic here. Only one small topic, that is double circuit transmission lines. Double circuit transmission lines. How to calculate GMD, GMR of that, and how to use it in the inductance calculation and the capacitance calculations. That we are going to discuss a little bit, and we will wind up this chapter and we will move to the main chapter, that is a steady state analysis of the system. Okay. Yeah. So I'm moving to the next slide. Next slide to take up the next heading, that is double circuit transmission lines. Double circuit transmission lines. Next heading. See, double circuit transmission lines, it's nothing but running two circuits two three-phase circuits on the same tower. Running two three-phase circuits on the same tower. Let me show. Let me show you. So this is a tower I am showing. Transmission tower. Transmission tower. Okay. So it's grounded. I can say like this. Grounded. And I'm showing cross arms on both sides. Cross arms on both sides. I'm going to show something like this. Yeah. So these are the cross arms I'm going to show. So this side also I'm showing cross arms corresponding to phase A, phase B, and phase C. Next, see, I will show here. I'll show here conductors of circuit number 1. Conductors of circuit number 1. I can say it is A1, B1, C1. Circuit 1 conductors. Three-phase circuit number 1. And here I am showing circuit number 2 conductors. A2, B2, C2. A2, B2, C2, and I am calling this one as circuit number 2 conductors. Circuit number 2 conductors. See, definitely these two circuits are running in parallel. There is no doubt about it. Both the circuits are running in parallel. Means, for example, if you want me to show, it's a phase A bus bar on the receiving sending end side, and it's a phase A bus bar on the receiving end side. And you have this line, phase A line, connecting this sending end side to receiving end side A1 and sending end side to receiving end side A2. So this is A1, A2. Okay. A1, A2. Similarly, phase B also B1, B2 will be repeated. B1, B2, right? So like this, you can say phase B bus bar, and then we have C1, C2, and this is a phase C bus bar. Okay, so I'll call A1, A2, and I'll say B1, B2, and this is C1, C2. So phase A, phase B, phase C. Phase A, phase B, phase C. So this side is a sending end side, and this side is a receiving end side for all cases. So both circuits are running in parallel. You can write here. I'll say in the next slide better. I'll say in the next slide the properties and to have more amount of, it's not bundle conductors. It's not bundle conductors. To have more amount of power transmission. To have more amount of power transmission, two circuits are required. To increase the power transmission capacity. Now, next, listen please. In double circuit line, two circuits are running in parallel. First statement. Both circuits are running in parallel. Okay. Next thing. Tell me, how will be the operating voltage of the two circuits here? How will be the operating voltage of the two circuits? Will it be equal or unequal? Operating voltage of the two circuits. Will it be equal or unequal? Tell me, please. Equal. As these two are running in parallel, definitely operating voltage will be equal. Both are operating at same voltage, or having same rated voltage. Also, you can see. Okay. So operating at same voltage. Both circuits operates at same voltage. Operates at same voltage. But how will be the current rating? How will be the current rating of the two circuits here? Anybody please tell me? How will be the current rating? Is it equal or need not to be equal? Need not to be equal. Current ratings are need not to be equal. Need not to be equal. Kindly check this word. Kindly check this word. Voltage ratings must be same. Voltage ratings must be same. But current ratings need not to be equal. Current ratings of the circuits are need not to be equal. Need not to be equal. Yeah, done. Need not to be equal. Next thing. So let us show practicality of the system a little bit for you. Already I have shown this diagram, I think. But still I am showing it. Just go through it. This figure I have shown. This double circuit line. I think this. Okay. So I think we can observe in this diagram itself as a double circuit line. Yes or no? Are you observing it? So if you want me to show, I will show that A1, B1, C1. This is other side, back end. This is one phase, second phase, third phase. Okay, so you can call it is A1, B1, C1. On this side, on the front side, this is A2, and this is B2, and this is C2. Like this, you can observe. So it is a best example for the double circuit line. It's one of the best example for the double circuit line. Not only that, it's a double circuit line. It's a double circuit line. Moreover, each and every conductor is a bundle conductor. Each and every conductor is a bundle conductor. So it's a three-phase double circuit bundle conductor system. Bundle conductor system. Three-phase double circuit bundle conductor system. So I think all of you getting this one. Yeah. Next. So let's continue. So just to give some more clarity, I will be discussing about different systems here. Just for the sake of heading only, I am taking it, different systems. After that, I will come back to this double circuit line. I will discuss in a brief way how to calculate GMR and GMD of this. Okay. Yeah. So let's move. Look here. Different systems. Saying different systems. First one. So I'll show a conductor something like this. It's A1. And I'll show B1 here. And A1 and A2. But these two are having a bit less gap. A1 and A2 will have some less gap between them. And same phase B I will repeat below. Phase B I have repeated here, phase B. And then phase C also I will repeat here. Phase C also I have repeated here. This is one system, you say. System number 1, you can call. System 1. Okay. And system 2, I'm going to show. System 2, I'm going to show. Just look here. So this is a A1 conductor of phase A. A1 conductor of phase A. And I'm going to show A2 conductor of the phase A with some good gap, good distance between A1 and A2. And I will repeat it as a phase B, repeating it as phase B. And then phase C, I'm going to keep like this. And this is a system 2. System 2. So system 3, I'm going to show system 3 in the similar lines. it's a conductor corresponding to phase A, conductor corresponding to phase A, and then conductor corresponding to phase A2 conductor is some large gap actually. Some large amount of gap I have shown. And then phase B I will repeat. Phase B I'm going to repeat something like this. And then phase C I will be keeping. Phase C I will be keeping up like this. So these are three systems. These are three systems. So in all cases, it is A1, B1, C1, circuit 1. Kindly observe my words, please. Kindly observe my words. A1, B1, C1, that's circuit 1. A2, B2, C2, and it's a circuit number 2 conductors next year. A1, B1, C1, circuit 1. A2, B2, C2, circuit number 2. And here again, A1, B1, C1, circuit 1. A2, B2, C2, circuit number 2. Yeah. Next. Distances, I will give some numbers directly to you. Numbers. A1 to A2, yes, 40 centimeters or 0.4 meters is at A1 to A2 gap. B1 to B2, C1 to C2 also. Phase A to phase B, D, 8 meters. And this also 8 meters. A1, sir, phase A to phase B, 8 meters, B to C also 8 meters. Let me show in the next case. This gap D, 8 meters. This gap is also 8 meters. And A1 to A2, this gap, yes, is something like 6 meters. A1 to A2 gap, I am showing like 6 meters. Next case. This gap D is 8 meter. And this also 8 meter gap D. And between A1 and A2, that gap is, let's say, 1 kilometer or 1000 meters. 1000 meters, 1 kilometer distance between them. Yeah. Very simple thing. Just answer it what I am asking you. Just answer it. System 1 you consider now. System 1. This is highly observable or what you have studied till now, strictly speaking. S value 40 centimeters. I am saying D is 8 meter. S value was negligibly small compared to D. Means circuit 1 to circuit 2 distance. Circuit 1 to circuit 2 distance is negligibly small. So as S is very, very low compared to D, what kind of system I will say this one? What kind of system I am going to say this? It's a bundle conductor system. So bundle conductor system. Not single phase, it's a single circuit, not phase, single circuit. Bundle conductor system. Bundle conductor system. Okay. Next you see, second one. A1, B1, C1, circuit number 1, A2, B2, C2, circuit number 2. How is the distance between circuit 1 and circuit 2? How is the distance between circuit 1 and circuit 2? It's not too low. We have a good amount of distance like 6 meters, maybe 10 meters. Observing the fact what I'm saying now. Between circuit 1 and circuit 2, there is a good value of distance, right? There is a good value of distance like 6 meters what we are saying here. See, listen. In the first one, circuit 1, circuit 2 we have. Just visualize the thing. Physically on the tower. How we are going to run system 1, system 2. How we are going to run the system 1 and system 2. For example, system 1 you talk, A1, B1, C1, circuit 1, A2, B2, C2, circuit 2, distance is very less. Where these two circuits will be running on the same side of the tower. I will keep A1, B1, C1, A2, B2, C2. Okay. Whereas second system, if you talk, distance between circuits is a bit good number. So on side one, I will keep one circuit, tower side one, circuit one, tower side two, circuit number two. Then this is going to be called as double circuit transmission line. Yeah. So have you understood this? Please tell me. Have you understood this? Yeah. So this is going to be called as double circuit line. Double circuit line where S is appreciable with respect to D. S is appreciable to D. Appreciable to D value. S is appreciable to D value. But here you observe that S value, what I said, 1000 meters, is very, very large compared to D. That S value was very, very large compared to D. So in this perspective, where the circuit one is running and circuit two is running on different towers, different tower one configuration, circuit one, tower two configuration, circuit number two. Okay, so this system we are going to call generally parallel transmission line system. This system we are going to call it as parallel transmission line system. Parallel transmission line system. Okay. See, you might be getting a doubt that, sir, you are saying the last one as parallel transmission line system. But for me, all are looking as parallel only. All the systems are looking as parallel systems only. Why you are specially indicating the last one as a parallel? That's a doubt generally the people used to get. I'll tell you the second one is also parallel system. Now I am asking one very simple question to you. In the system two, do you have any appreciable mutual linkages from circuit one to circuit two? Do you have any appreciable mutual linkages between circuit one and circuit two? Yes or no? Definitely, because the distance is less. Appreciable. Okay. Third system. Can we have appreciable mutual linkages between circuit one, circuit two? Third system. Can we have any mutual linkages? Appreciable? No. So I'll write here in bracket, no mutual linkages. No mutual linkages between circuit one and circuit two. Between circuit one and circuit two. But here, mutual linkages exist between the circuits. Mutual linkages exist between the circuits. Exist between the circuits. Yeah. So let's move to inductance per phase formula for double circuit line. Exclusively, we are talking about double circuit line. Double circuit line. For double circuit lines. Inductance per phase formula, same as earlier one. 0.2 natural logarithm GMD by GMR. GMD by GMR, and this will be in terms of millihenry by kilometers. 0.2 ln of GMD by GMR in terms of millihenry by kilometers. Okay, kindly listen to me. I'm saying bundle. Anyway, I have written formula for double circuit line, that's okay. But I'm talking about bundle now. Talking about bundle. What is GMD of this system? What is GMD of this one? Can I say it is cube root of 8 into 16? I need your answer, yes or no. I need your answer, yes or no. Yes. So it will be cube root of 8 into 16. That's it. Okay, what is GMR? GMR is nothing but simply R dash into S value. R dash into S value under root. R dash into S value under root. Okay, done. Second one, double circuit line. Listen to me, please. Double circuit line. What is GMR of phase A? What is GMR of phase A? Can I use the same formula root of R dash into S? GMR of phase A, can I use the same formula root of R dash into S? Yes, same formula can be used. Same formula can be used. No change. Same formula can be used, but number may be different. Number may be different. Okay. What about GMD of this one? What about GMD of this one? Can I say this GMD cube root of 8 into 8 into 16? Can I say GMD of this one? Cube root of 8 into 8 into 16. Yes or no? No, we can't say that. We can't say that. Why it is so means in the earlier case, listen all of you, listen all of you. In the earlier case, I have written the GMD as cube root of 8 into 8 into 16. Cube root of 8 into 8 into 16. Why in the sense? SC is very, very less compared to D. SC is very, very low compared to D. Because of that assumption, you can write it safely as cube root of 8 into 8 into 16. But here, SC is an appreciable number with respect to D. SC is an appreciable number with respect to D. In this case, you can't write it as simply cube root of 8 into 8 into 16. Following here, S value must be taken care into the GMD calculation. S value must be taken care means S value we no need to take up directly to GMD. We should appreciate the distance between the circuits. Okay. So in that way, we have some difference in the calculation of GMD for double circuit line compared to bundle. GMR calculation will be as it is. Calculation wise, it will be as it is. But GMD, we have some difference in the calculations. Yeah. So let's consider or let's proceed with the double circuit line. Let's proceed with the double circuit line. Let's take first GMR calculation. GMR calculation for double circuit line. GMR calculation. So all of you listen to me. I'll show this original double circuit line. What we have? This one. Look this one. Look this one, please. Radius of the conductors might be equal most of the times in circuit 1, circuit. Circuit 1, circuit 2 might be having equal radius, but still I am showing some difference. Circuit 1 conductors, R1 is a radius. Circuit 2 conductors, R2 is a radius. R2 is a radius. Currents, kindly observe the currents. A1, I1 at an angle 0. B1, I1 at an angle minus 120. C1, I1 at an angle plus 120. A2, I2 at an angle 0. B2, I2 at an angle minus 120. C2, I2 at an angle plus 120. How many phases we have? Anybody? Anybody, please tell me how many phases? How many phases we have? 3, not 2, 3. Check here kindly, not 6 also. 3. A1, A2 phase A, B1, B2 phase B, C1, C2 phase C. 3-phase system already have mentioned, right? See, if you have 3 phases here, like phase A, A1, A2, phase B, B1, B2, phase C, C1, C2, you take up GMR of the phase A, GMR of the phase B, GMR of the phase C. GMR A, GMR B, GMR C. Geometric mean of these 3 GMRs will be GMR of the system to be taken up in the inductance per phase calculation. Inductance per phase calculation. So I can say GMR is nothing but phase A, phase B, phase C, GMRs, phase A, phase B, phase C, GMRs under cube root. So it will be cube root of GMR A, GMR B, GMR C. Let's take GMR A quickly. GMR A quickly. Just listen to my words. Listen here. Only A1, A2 we have to take. Only A1, A2. I didn't kept any S values or D values here. S values or D values here. Just look at this in this manner. If you want to take distance between A1 and A2, A1, A2. You write it as DA1, A2. Right? That DA1, A2 rather than confusing with S and R. Okay. Similarly, B1, B2 distance you want, you take D, B1, B2. C1, C2 you can take D, C1, C2. For example, if you want to have from C1 to A2, C1 to A2, you write C, D, C1, A2, D, C1, A2. Like that you proceed. Okay. Next one. Listen. Self distances of A1 will be R1 dash into DA1 A2. R1 dash into DA1 A2. Okay. So I'll show here R1 dash into DA1 A2. These are the distances of A1 conductor. What about for A2 conductor? A2 conductor R2 dash into DA2 A1. R2 dash into DA2 A1 for A2 conductor. R2 dash into DA2 A1 for the A2 conductor. And total how many numbers we have now? Total how many numbers? 4 numbers you have as a total. And this whole power 1 by 4 you should call. Whole power 1 by 4. That's the GMR of the phase A. Next one. GMR of the phase B. GMR of phase B. Check this one now. Phase B. R1 dash. DB1 B2. Okay. For B2. R2 dash. DB2 B1. R1 dash. DB1 B2. Next one is R2 dash. DB2 B1. Whole power 1 by 4. This is GMR of the phase B. Next, GMR of the phase C. Check here, phase C. R1 dash, DC1 C2. Next for C2. R2 dash, DC2 C1. R1 dash, DC1 C2. R2 dash, DC2 C1. This whole power 1 by 4. Whole power 1 by 4. We are showing the conductors on the same tower, not tower to tower. We are showing conductors on the same tower, not the tower to tower. Okay, let's think about the GMD calculation quickly. Let's think about the GMD calculation quickly. GMD calculation, we will say. Calculation. Yeah, you see this. GMD, basically for a three-phase system, GMD is nothing but cube root of DAB, DBC, DCA. Forget about how many conductors you have in the phase A, phase B, phase C. Forget about how many conductors you have in the phase A, phase B, phase C. Just to take it as cube root of DAB, DBC, DCA. That's it. So let's say GMD of the system here is nothing but cube root of AB distance, BC distance, and then CA distance. AB distance, BC distance, and then we have CA distance. Not only that, as phase A is consisting of 2 conductors, B is having 2, C is also having 2. Let me write in some way that it is DAB equivalent gap, effective distance between phase A and phase B. Effective mutual distance between phase A and phase B. Effective mutual distance between B and C. Effective mutual distance between C and D. Effective mutual distances between A and B, B and C, C and A, we can see. C and A. So let's say DAB equivalent now. DAB equivalent. DAB equivalent. Just kindly observe. Kindly observe. Very simple thing. Just listen. Don't commit a mistake. Just listen. Just listen here. Don't ask me a doubt again. Just listen. See, if you want to check that AB gap, we should take only phase A and phase B. That's it. You should not take the C conductors at all. You should not take the C conductors. Why? We have to get the distance between phase A and phase B. That's the reason. Okay. Now, tell me please. Tell me please. See, for example, beside A1 conductor, I need your answer please in this group of AB phase, beside A1 conductor, how many conductors are available? Beside A1, how many conductors are available in that group? Three conductors are available beside A1 in this group. But whatever the conductor A2 we have, that's the self of A1. Conductor A2 is the self of A1. Then obviously, how many mutual conductors are existing for A1 now? How many mutual conductors are existing for A1 now? Only two. That is B1 and B2. Only two, that will be B1 and B2. Now I'll tell you distances. Simple mutual distances. A1 B1, A1 B2. A1 A2 we should not take. A1 A2 we should not take. A1 B1, A1 B2. That's it. Next, for A2. A1 is self. Then we should take mutual distances from A to B1, A to B2, A to B1, A to B2. Total how many distances we have? Total 4 distances we have. Geometric mean of these 4 numbers will be DAB equivalent distance. Total 4 distances. Geometric mean of these 4 numbers will be effective mutual distance from phase A conductors to phase B conductors. Okay, so I'm writing it. Just go through this term. A1 B1 gap, A1 B2 gap, A2 B1 gap, A2 B2 gap, whole power 1 by 4. Whole power 1 by 4. That's a DAB equivalent. Next one. What is the BC equivalent here? What is the DBC equivalent? Anybody? DBC equivalent. This one we are thinking. This one, BC. B2C. Now we should take B1C1, B1C2, B2C1, B2C2. Okay. So I can say here. So DB1C1, first one. DB1C2. DB2C1, DB2C2, and 4 numbers you have, whole power 1 by 4. Next, DCA equivalent. What you can say DCA equivalent? C1A1, C1A2, C2A1, C2A2. Effective distances from phase C to phase A conductors. Okay. So you can call here C1A1, C1A2. And you can say C2A1, C2A2. And this whole power 1 by 4. So after getting these three, DAB, DBC, DCA, substitute these 3 numbers into this equation and we will get the GMD of the system. We'll get the GMD of the system. Yeah. So this is the end of the double circuit lines. So we'll close this chapter by this point. We are going to close this chapter by this point, second chapter. So then we are going to start with the next chapter, that is steady state performance analysis of the transmission lines. Steady state performance analysis of transmission lines. So I've shown 143 slides. Somebody asked me to show 143 slide. See that DA1, A2, DB1, B2 will not come. DA1, GMR for the double circuit we discussed it right already. GMR for double circuit already we have discussed. Okay. DA1, A2, B1, B2 already taken in the GMR. Moreover, those values are self distances, which won't come in the mutual calculations. Mutual calculations. Yeah. So let me close this. What is proportional to square? Proportional to square, what is that? In parallel transmission line, L will be independent for each circuit. L you can calculate for circuit 1 and circuit 2. Then you can connect the two inductors in parallel and you can get it. How Kepler and small r are inversely proportional. Already you know Kepler is inversely proportional to area of cross section, right? Kepler is inversely proportional to area of cross section. Area of cross section means pi r square. Pi r square. So Kepler will be inversely proportional to radius square. Transposition will be done even for double circuit lines. Transposition is done even for double circuit lines. So I have opened the next chapter slide, that is steady state performance analysis of the transmission lines. Yeah. So this is one of the important chapters to be discussed further. Steady state performance analysis of transmission lines. Okay, so let's see what is the aim of doing this steady state performance analysis of line. Aim. What's the aim of doing this analysis? See, very simple, very simple. The aim here is to know whether that line is working satisfactorily or not. Whether the line is operating satisfactorily or not at a given loading condition. Right? So to know whether the line is operating satisfactorily or not satisfactorily or not at a given loading condition. At a given loading condition. Loading condition. To know whether the line is operating satisfactorily or not at a given loading condition. Okay. This point is very, very important for us. A given loading condition is very, very important for us. Means to say whether the line is operating satisfactorily or not, definitely you should tell me what is the amount of load. What's the amount of load at which that line is going to operate. That you have to tell. Okay. Next thing. Next. See, to know performance of the system, to know this performance of transmission line, generally we have some performance indices. Performance indices. Two indices we have here. Performance indices. Performance indices. Indices. First one we are saying efficiency. First one we are calling as efficiency. Second one we are going to call as regulation. Second one we are going to name it as regulation. Okay, first one we are saying efficiency and second one we are saying as regulation. Efficiency. It's of two kinds. One, power efficiency. Next one is a energy efficiency. Okay, efficiency is of two kinds. First we are naming it as a power efficiency. And second one we are going to call it as energy efficiency. Energy efficiency. Two kinds we have, power efficiency and energy efficiency. The next one. Regulation. We have two. One is a static regulation. Next one is a dynamic regulation. Okay. Regulation, I can say it's up to first one. Static regulation. Second one, we are calling it as dynamic regulation. Dynamic regulation. Two types we have here. One is a static regulation. Next one is a dynamic regulation. Next thing. Listen, please. Listen. See, among these two, power efficiency and energy efficiencies, this energy efficiency will be used for the distribution transformers most of the times. For the distribution transformers, like you might have studied all-day efficiency, right? So this is used for distribution transformers. Whereas the power efficiency will be used for all other remaining apparatus. So as far as our transmission line is concerned, we will be concentrating on the power efficiency calculation only. We will be concentrating on the power efficiency calculation. Okay. Next thing. If you talk about regulation, we have two kinds. One is static, next one is a dynamic. See, static regulation, it is to be done for apparatus which are giving electrical power as output. Okay, so it's done for apparatus giving electrical power as output. Is done for the apparatus giving electrical power as output. Okay, and whereas this dynamic regulation, it is done for the apparatus which are giving mechanical power as output. Done for apparatus giving electrical power, mechanical power as output. Done for the apparatus giving mechanical power as output. So next thing, please. See, if you look at the apparatus now, like if you see generator, let's say generator, which regulation we calculate for generator, static or dynamic? Generator, which regulation we calculate, static or dynamic? Static, because output is electrical, right? Output of generator is electrical, so we have to go with the static regulation for the generator. And if you say for transformer output is electrical, so we have to go with static. Line output is electrical, we have to go with the static. But if you go with motors like synchronous motor, induction motor, and so on, for those motors, we have to go with the dynamic regulation. Unless otherwise, remaining all apparatus will be going with the static regulation only rather than the dynamic regulation. Okay, let me tell you this one. Very simple thing. This static regulation, electrical power output. So I am saying this P is equals to V into I cos P. Power, real power, P is equals to V into I cos phi. Now, I am asking one very, very simple question. Assume that this power factor is a bit constant. Assume that cos phi value is constant. Now, if the real power demand value was increased or changed, whatever it is, real power demand value was increased, what will happen to this voltage and current? What happens to the voltage value? What happens to the current value? Anybody please tell me? Voltage value will be more or less same. Voltage value will be more or less same, but current value is going to be increased. Current value will be increased. That increment is going to meet the power demand. But this voltage is almost same. But definitely, certain variation we can expect in the voltage because of the load change. Definitely, certain variation we can expect in the voltage because of the load variation. Okay, how much change in the voltage we are going to get? That is described by the static regulation term. That is going to be described by the static regulation term. Hence, we are going to call the static regulation as voltage regulation. Okay, so the static regulation can be called as voltage regulation. Static regulation can be called as voltage regulation, and whereas this dynamic regulation can be called as speed regulation. Okay, dynamic regulation can be called as speed regulation. Next. So for our transmission line, as we are saying now, for our transmission line, we are thinking about two indices. One, it's a power efficiency. Second one is obviously voltage regulation, or you can say static regulation. Let's define these two terms, power efficiency and voltage regulation. Before going to the definition, let me recall the equivalent circuit, what we have drawn earlier. For the transmission line per phase. Let's take. See, for example, it is a practical transmission line, what we are seeing on the towers, let's say. Practical line, what we are seeing on the tower. And it's the input side and its output side. Input side and output side. And you see this line, we are going to keep with some series element as well as some shunt element. That's what we have seen in the previous chapters, right? Series elements are L, shunt elements will be CG, according to the properties of line. We are placing these things. So I can say for this line, I am showing RL series and shunt will be CG. So like this, you can see RLCG. And this is the input side. Input side can also be called sometimes as sending end side now. Input side can be called as sending end side. And output side can be called as receiving end side. Output side can be called as receiving end side. Notations. Sending end side voltage and currents, PSIS. Powers, PSQS. Receiving end side voltage currents, VRIR. Powers, PRQR. PRQR. Powers. Next thing, one small thing we have to know. Input side means we might be having one generator. Output side means we might be having a load. Output side means we might be having a load. Now the question is, which is dependent and which is independent? Yeah, please tell me which is dependent and which is independent here. All of you. Dependent and independent. Okay, listen please. For example, if my load demand is, let us say 30 megawatt. Very simple question. If my load demand is 30 megawatt, how much amount of power this generator has to supply? Assume that there is no loss. There is no loss. Okay. How much power the generator has to supply? Definitely 30. Generator has to supply 30. Okay. Yeah. So let's say this has to supply 30 megawatt. Now, all of a sudden, I have increased this power demand from 30 to 40. I increased the output or power demand from 30 megawatt to 40 megawatt. Then, obviously, this generation will be increased from 30 to 40. That generation will be increased from the value 30 to 40. Tell me now, without disturbing this load, is it possible to increase the generation from 30 to 40? Without changing the load, is it possible to increase the generation from 30 to 40? Yes or no? No, it is not possible. Means, obviously, you can say the generation side will be dependent on the load variations. Means sending end side will be dependent on the load variations, we can say. Okay, so I can say this side is dependent on the load variations, and receiving end side you can name it as independent. Receiving end side we can name it as independent. Okay, so I think all of you getting this clear? Next, let's move with the definitions of power efficiency and regulations. First term I'm going to take up, that is power efficiency. First term I'm going to take up, that is power efficiency. It's very simple one. It's output power by input power. Output power by input power. Or else you can say output power by output power plus power loss. Output power by input power. Else you can say this one as output power by output power plus power loss. Output power by output power plus power loss. Okay. Next thing. That output power is nothing but receiving end side demand. Input power is PS, which is nothing but receiving end side power plus power loss. Receiving end side power by receiving end side power plus power loss. Okay. What is power loss equation? What is that power loss equation? See, you have two losses in this system, right? Just observe now in this diagram. In this diagram, you can say we have two losses. One is loss due to resistance. Next one, loss due to shunt conductance. Loss due to resistance. Next one is a loss due to shunt conductance. Okay, what is the loss due to resistance? I square into R. I square into R, you can say. Loss due to conductance is what? V square into G. V square into G. Okay, so I can say here 2 things we have I square R loss plus V square into G loss. Two losses we have. One is I square R, next one is V square into G. V square into G. It's a power efficiency definition. Next one, let's think about the voltage regulation definition. Let's think about the voltage regulation definition. Voltage regulation. Definition of voltage regulation. Yeah, we'll neglect it, Shiva. We'll neglect it just as a circuit we have considered now. Listen, please. Listen. Voltage regulation. So, what is the definition of voltage regulation generally? What will be the definition of the voltage regulation generally? Okay, let's show some circuits here in a sequence. First one, I am showing one transmission line here. So, given something like this transmission line wire. Okay. So, input side we have a source. I'll show one source here. And this is Vs. Source here it is Vs. Output side we are keeping a load, that's VR. It's a load with certain power factor cos phi r. So its output side, you can say this voltage as VR. You can say that voltage as VR. Transmission line. It's a transmission line. It's a case one. Case one. Case two, I will repeat same. Repeating the same. Repeating the same. In the case two, repeated the same. But whatever the load we have, that load I am disconnecting. Whatever the load we have, that load we have disconnected. Or you can say load is suddenly thrown off. Load is suddenly thrown off, and this is going to carry zero current. That's going to carry zero current. At that time, whatever the receiving end voltage of the line we have, whatever the receiving end voltage of the line we have, that let me denote with a letter VR0. No load receiving end voltage of the transmission line. No load receiving end voltage of the transmission line, I am denoting it. Yeah. Okay, no load receiving end voltage. Now, let me give you the exact definition of the voltage regulation. So, exact definition of voltage regulation will come like this. Voltage regulation. You see, it is the change in the receiving end voltage magnitude. Change in the receiving end voltage magnitude. Receiving end voltage magnitude of transmission line. Magnitude of transmission line. When a load is suddenly thrown off or disconnected. When a load is suddenly thrown off or disconnected. Okay, so it's a change in the receiving end voltage magnitude of the line, when a load is suddenly thrown off, or you can say disconnected. Comma, measured with respect to load voltage magnitude. With respect to load voltage magnitude. Measured with respect to load voltage magnitude. Yeah, please listen. Please listen here. So I have given two diagrams here. One is with loading, next one after removing the load. One with loading, next one is after removing the load. My question is very simple. According to this definition, it's a change. It's a change rather than change. Better I'll say rise, rise. Kindly modify that word. It is a rise, rise or increment, increment in the receiving end voltage magnitude of the line when the load is suddenly thrown off. When the load is suddenly thrown off, measured with respect to load voltage magnitude. That's so according to this statement, which is a case 1 and case 2. With load, without load, you have two cases, right? Okay. So I'm asking you, which is case 1 among these two? Is it with load or without load according to the definition? According to the definition, which is a case 1? Is it with load or without load? Obviously, it is with load. With load means you should understand in this way. You should understand in this way. Already the line is operating with some load, having certain voltage at the receiving end side. Now that load was suddenly thrown off. Load was suddenly thrown off. Voltage was changed. How much is that rise in the voltage you got? How much is the rise in the voltage you got after disconnecting the load? That magnitude change with respect to load voltage magnitude is that voltage regulation. Okay, so that magnitude rise here, listen please, listen please. With load, I'll say VR, something like mod VR at an angle theta1. And VR0 after disconnecting the load, it is something like mod VR0 at an angle theta2. What is it? Rise in the voltage magnitude now? Rise in the voltage magnitude. Mod VR0 minus mod VR. Mod VR0 minus mod VR. That's a rise in the voltage magnitude. That we should divide with the load voltage magnitude. Mod VR. And this is going to be called as voltage regulation. If you want to get it in percentage, you should multiply with 100%. Like this, you can say voltage regulation. Voltage regulation. Rise in the receiving end voltage magnitude when the load is suddenly thrown off means mod VR0 minus mod VR by mod VR into 100%. Yeah, done. Next thing. So let's have a break of 5 minutes. So after break, we will be moving on to classification of transmission lines. Classification of transmission lines and the procedure, how we are going to discuss that I will tell you. Okay. So I am showing our last slide. Okay. So then it's a 6F. So 5 minutes break. Square G, loss name is loss due to leakage current and loss due to corona. All these things will come. So I have resumed the audio, video, and screen. Resumed the audio, video, and screen. So kindly tell me. So audio, video, and screen, is it okay? Fine, fine, good. Next. See, this is a way how we are going to discuss this chapter further. This chapter. First, we are going to discuss about classification of transmission lines. Classification of transmission lines we'll discuss first. So after that, we will see the equivalent circuit of each and every line. Equivalent circuit of each and every line. And then we will be introducing ABCD parameters. We'll be introducing ABCD parameters, which makes our steady state analysis a bit simple. Steady state analysis a bit simple. After completing ABCD parameters, we will come back to the classification of lines and we'll take up each and every line and we'll try to calculate ABCD of that and we'll make some comment on the voltage regulation. Following all of you? Just listen. I am repeating the statements. Kindly follow it. Kindly follow it. See, first we are going to take up the classification of lines. Then equivalent circuit of each and every line. Then ABCD parameters. And then we'll come back to classification of lines. And we'll take up each and every line. And we'll find out the ABCD parameters and we'll make some comment on the voltage regulations. Okay. So let's see first one. Classification of transmission lines. Classification of transmission lines. Classification of transmission lines. First of all, you should know what is a criteria. What is a criteria or on what basis you are going to do this classification. That we should know first. Anyway, tell me, what is the criteria for the classification of lines? Criteria for the classification of lines. In various textbooks, you can see in various criteria. One thing what I can say is, this classification is done on the basis of physical length of transmission line wire. Physical length of transmission line wire at a given operating frequency. Okay. So done on the basis of physical length of line, physical length of line at a given frequency, at a given frequency, a given operating frequency. Physical length of line at a given frequency. This is one criteria. And second criteria I'm saying now, second criteria I'm going to say, it is done on the basis of consideration of capacitance into equivalent circuit. Is it required to take the capacitance into circuit or not? Is it required to take the capacitance into circuit or not? That is one basis for the classification of lines you can see. So, according to the consideration of C into equivalent circuit, capacitance into equivalent circuit, done according to the consideration of capacitance into equivalent circuit. Next criteria you can see, done according to the magnitude of the charging current, done according to the magnitude of charging current, magnitude of charging current. Okay. What is the charging current? And what quantities this IC value will be depending? Charging current value will be depending. You know, IC, yesterday class we have discussed, proportional to IC, proportional to voltage, frequency, capacitance. Charging current is proportional to voltage into frequency into capacitance. Not only that, that capacitance is capacitance for total length of transmission line wire. That C is a capacitance for total length of the transmission line wire. Else, it's better to say capacitance per kilometer multiplied with the length. capacitance per kilometer multiplied with the length. Okay. So V into F into C. V into F into C, you can say as V into F into C per kilometer multiplied with the length. But listen, capacitance per kilometer of a 132 kV line and capacitance per kilometer of a 220 kV line. Can I say both are having same values? Capacitance per kilometer of 130 kV line and 220 kV line. Can I say both are having equal values? Yes or no? Almost. Yesterday, that's the comment we have made, right? That's the comment we have made in the capacitance calculation in the previous classes. So this C per kilometer is almost constant. This C per kilometer is almost constant. So from this point onwards, I used to say this charging current mainly depends upon operating voltage, frequency, physical length of line. So I can say now this charging current mainly depends upon voltage, frequency, length of the transmission line. Okay, let's come back to this criteria. What we have written, 3 criteria. Which criteria we are going to take among these 3? So I used to prefer all the time the last criteria what we have here. According to the magnitude of the charging current. Why it is so means charging current is a term which will cover all. Operating voltage it will cover, frequency of operation it will cover, as well as physical length of line also it is going to cover. But actually, the second one and third one looks to be same. According to the consideration of C into circuit, now who will decide whether to take that capacitance into circuit or remove capacitance from circuit? Who will decide it? That will be decided by charging current magnitude. If the charging current is negligibly small, then you no need to take C into circuit. If charging current is appreciably high, definitely we should take that capacitance into equivalent circuit. Following all of you. So the charging current value mainly depends upon these 3 things: voltage, frequency, length of the transmission line. Okay, right. So next I can say 3 types of lines now. 3 types of lines. One is a short line, which has very negligible value of charging current. Medium line having an appreciable value of charging current. Long line having a good amount of charging, good value of charging. Okay, so I can say in the classification of lines, first one I am saying short transmission line. You can call it as charging current is negligibly small. Negligible. IC is negligible. Second one, medium transmission line. Charging current is appreciable in number. Third one, long transmission line. Charging current is high. In value. Okay, done. Next. Charging current is line current. Line charging current and both are same. Line charging current only we are discussing, no Shiva? Let's continue now. Let's assume that frequency is constant at 50 Hz. Now you please tell me, after saying that the frequency is constant, charging current depends upon what factors here? Operating voltage and length. These 2 things are mainly deciding the charging. Particularly, charging current will be negligibly small for a length less than 80 kilometers. As well as operating voltage less than 20 kV. Operating voltage less than 20 kV, length less than 80 kilometers, right? Then the charging current is negligibly small. You can take that line as a short transmission line load. Following. And in between 80 to 160 kilometers, whereas operating voltage in between 20 kV to 100 kV, 20 kV to 100 kV, and this charging current is an appreciable number, we are going to take that line as medium transmission line. Medium transmission line. Okay, long line means length greater than 160, length greater than 160, operating voltage greater than 100 kV. Operating voltage is greater than 100 kV. 100 kV. Okay. So let's say in the next slide, I am saying, next slide. You see, we have one transmission line like this. Transmission line. That line we are modeling with some series elements of RL and with a shunt element of capacitor like this. Yeah, look here, please. It's a sending end side and this is a receiving end side. Sending end side, we might be having a source, you know. Receiving end side, you might be having some load like this. Load. And this is your series impedance Z, and this is a shunt admittance Y. Series impedance Z, shunt admittance Y. A G can be neglected. We have neglected the G right now in this circuit. In this circuit, we neglected the G for time. Okay, listen to my words, please. Listen to my words. I know receiving end voltage VR and receiving end current as IR. After knowing it, you are capable to find this charging current IC. Then you will get this current something like IR plus IC. And after applying KVL, you are going to get the sending end voltage as VDC. Very simple analysis, network analysis. You know receiving end voltage, we find out charging current. And IR plus IC is flowing in this series branch. Okay, apply KVL for this loop so that we can get the sending end voltage as Vs. Sending end voltage, we are going to get it as Vs. Okay, next thing. Next thing. See, if the charging current is negligibly small, very simple analysis, very simple, don't complicate, very simple analysis. The charging current is negligibly small, then obviously this IR plus IC what we have now, this IR plus IC what we have now, this you can write approximately as IR. The charging current is negligibly small, this IR plus IC, we can approximate it to IR. Means my interest is to tell you, the charging current is very less. Even though you consider that into the analysis or neglect it from the analysis, it makes no difference in the final result. It makes no difference in the final result. All of you getting this one, what I am saying you? The charging current is negligibly small. Even you consider that into the circuit or remove the capacitor. Remove the capacitor from circuit. There won't be any change in the final result to be considered. Okay, so in that perspective, which is easy for you? Is it considering capacitor into circuit or neglecting capacitor? In the analysis or mathematical calculations, which is easy for you? Removing capacitor will be easy. Removing capacitor will be easy. So that for short length of lines, if the charging current is negligibly small, I can say capacitance can be removed from the circuit. Removed from the circuit. C can be removed from the circuit. Once after removing that C from circuit, what this network is consisting? Only RL. It will be consisting only RL. So this we are going to name it as RL lumped parameter model of representation. This we can say it as RL lumped model representation of transmission, represented only as a series impedance, or you can say series impedance representation. Series impedance representation. Representation, you can say. Okay, next, if you think about the medium line, medium transmission line, simple. Yeah, so lumped in the sense, we will discuss after completing these two. Just listen. Second one, medium line. IC is appreciable. If IC is appreciable, definitely we should take that capacitor into circuit. There is no choice for you, because if you remove the capacitance from circuit even for second case, your result may not be accurate. Results may not be accurate. So capacitance should be taken into circuit. C must be taken into circuit. Taken into the circuit. So after saying that C must be taken into circuit, I can say this model as RLC, lumped parameter model. RLC, lumped parameter model. And we have a series branch as well as we have a shunt branch for the transmission line analysis. We have a series branch as well as we have a shunt branch. Okay, next one. Long transmission line, charging current is high, so there is no other choice for you. Capacitance should be taken into circuit. C must be taken into circuit. Must be taken into circuit. And I will call this one particularly as RLCG distributed model. RLCG distributed model. So don't bother about this G actually. Don't bother about this G. If they have given, we will take it into circuit. If they have not given, we can neglect. That's a small rule we have to follow. If they have given it, we will take. If they have not given, you neglect. But in general, I am saying this one. RLCG distributed model representation for the transmission line. Okay. Yeah. Next. See, from these things what we have discussed, three types of lines: short line, medium line, and long line. I can say in a simple way. The transmission line can be represented. Listen to my words, please. Transmission line can be represented in two ways. One, in the lumped parameter model. Second one, distributed model. Okay, two models of line representation I can have. Two models of line representation. One is lumped, next one is a distributed. Then what is this difference? Lumped model means what? Distributed model means what? See this. For example, if you have a line of 100 kilometers length, let us say, listen to me, listen, very simple thing. 100 kilometers length of transmission line wire we have. So we calculated the resistance value per kilometer, inductance value per kilometer, capacitance value per kilometer. So RLC we calculated per kilometer. Multiply that with the length of line. Multiply these numbers with length of line. I will get total resistance per 100 kilometers, total inductance per 100 kilometers, total capacitance per 100 kilometers. The total resistance per 100 kilometers, we will keep it only one place in the circuit. We'll keep that at only one place in the circuit, something like this. That is lumping. Okay, rather than keeping that resistance value for each and every kilometer, we are combining the whole resistance of line and we are keeping that at only one place on the paper. Okay, so total inductance at only one place, total capacitance at only one place. This model we are going to name it as lumped parameter model of transmission line. This model we are going to say it as lumped model of the transmission line. Okay, so I think all of you getting this lumped model. But if you talk about the distributed model, you don't have exact network representation for the distributed model. You don't have the exact network representation for distributed model. Let me write distributed model. Distributed model. So no exact network representation. Strictly speaking, this distributed model is going to be represented in the form of mathematical equations. Okay, so represented. You write here better. Exact distributed model means exact distributed model means it is represented in the form of mathematical equations. Mathematical equations. Represented as mathematical equations. Exact distributed model. But for the approximate sake, just listen to me. For approximate sake, what we'll suggest is, in case of distributed model, total length of line, you divide into number of small sections. Let's say 200 kilometers length. 200 kilometers length. So 200 kilometers length, I made 200 sections. 200 sections. Each section 1 kilometer. That each 1 kilometer you keep in lumped model. And connect all these 200 lumped models in the cascade. So that will give an approximate distributed model representation of the line. Okay, so in the approximate distributed model, I'll write approximate distributed model. I can say total length of line divided into number of smaller sections, total length of line divided into number of smaller sections, comma, each section represented as a lumped model, and all these sections are connected in cascade. All these sections are connected in cascade. All these sections are connected in cascade to form approximate distributed model. To form the approximate distributed model. Yeah, so I think all of you getting this. So now I'll try to show that model. In the next slide. Approximate distributed model. Yeah, see this. So it's a first section I'm showing. RLCG, first section. So like that, we have number of sections to be connected in cascade, I am saying. Number of sections to be connected in cascade. Okay. And this is for the complete length of line. Yeah. RLCG, circuit parameters. So this is approximate distributed model. Next thing. Next thing. Yeah. So this is C and G capacitor, and this is a shunt. Fine. So these are per kilometer values of RLCG. Okay, let's move back. To the representation of lines, what we have written. Two models we are saying now. One is a lumped model, next one is a distributed model. Lumped model and distributed model. Generally, we used to practice two types of analysis on any system. Either it is a transmission line, transformer, anything. Two types of analysis we used to carry. One is a steady state, next one is a transient. Steady state, next one is a transient. See, listen. Whenever you are doing the steady state analysis, you have to represent that line in the lumped model. You have to keep that line in the lumped model. And whenever we are doing transient analysis, we have to take only distributed model representation of the transmission line. Okay, so that point we have to note it down. I can say here, for steady state analysis, lumped model has to be used. Lumped model has to be used. Second one, transient analysis. We have to use a distributed model. Distributed model has to be used. Okay, transient analysis, we have to use a distributed model. Distributed model has to be used. Okay, so next, we have some deviations here. Just try to listen whatever I am saying you, and at the end you are going to get a good clarity about this classification of lines, why we are doing all these things. Okay, yeah, let's see now. For example, we have a line of 50 kilometers length. Let us say we have line of 50 kilometers length, something like this. Length of the line is 50 kilometers, and we are keeping one voltage source on this side. Listen to my words kindly. I will be closing this switch at time t equals to 0 plus. Closing the switch at time t equals to 0 plus. Means what analysis we are going to carry on this one? Transient. We are going to carry the transient analysis on this transmission line, because switching transient study we want to carry on this. So we are going to do the transient analysis. See, listen. While you are doing transient analysis, which model you should take for line representation? Which model you should take for the line representation while you are doing transient analysis? Distributed model we should consider. Please kindly listen my words. 50 kilometers length of line. We are doing transient analysis. Line is going to be represented in the distributed model. What type of line it is? Is it short, medium, or long? Which line? Anybody, please tell me. It's a long line. It's not short. It's a long line. Why? In the sense, which model we are using here? Which model we are using for the line representation? Distributed model we are using. Once if we are using distributed model, the line must be called as long transmission line only. But you are saying the length of line is 50 kilometers only here. But here, with respect to this, the length must be more than 160. Then what is this classification they have given? Length less than 80 kilometer, go with RL lumped model. 80 to 160, go with the RLC lumped model, and more than 160, go with the distributed model. What is this classification that people have given? This classification they have given in the view of the steady state analysis, right? This classification they have given under the steady state analysis. As far as the transient analysis is concerned, the line must be represented only in the distributed model. Line must be represented only in the distributed model. All of you getting this one? So this classification is valid only under steady state. I'll write here only under steady state. Only under steady state. I have written here. Kindly adjust with that. Only under steady state. Okay, done. Next thing. Let's continue. In this way, analysis. 50 kilometer length of line. Just listen my words, please. Listen my words concentrately. 50 kilometer length of line. I want to do steady state analysis now. 50 kilometer length of line. I want to do the steady state analysis. Which model we have to use? Which model you suggest? You suggest to go for RL lumped model. You suggest to go for the RL lumped model because it is less than 80. Okay. Can we do the analysis of 50 kilometers length of line, 50 kilometers length of line by using RLC lumped model? Steady state. Can we do that 50 kilometer length of line steady state analysis by using RLC lumped model? Yes or no? Yes, you can do it. There is no mistake in that, right? Your analysis will be even more perfect, right? Your analysis will be even more perfect. Maybe laborious, that's okay. But still, you can go with RLC lumped model. There is no mistake in that. So the same 50 kilometer length of line steady state, can we do it by using distributed model? Yes, this is an exact model of line representation all the time. Distributed model will be the exact model of the line representation all the time. Okay, so this is exact model of line representation. Next one. I have a line in between 80 to 160. Listen to my words. Line between 80 to 160. Okay. Which model the people are suggesting? RLC lumped model they are suggesting. RLC lumped model. Can I go with RL lumped model? In the span of 80 to 160 steady state analysis, they are suggesting us RLC lumped model. Can I go with RL lumped model? Yes or no? No, we should not go. Yes or no? We should not go. Can I go with the distributed model? Yes, because it's the exact model of line representation all the time. Okay, so whereas length more than 160, we should go with only distributed model of line representation all the time. You please tell me now, what are these three? Whether these three are different types of lines or different equivalent circuits for the transmission line. Whether these three are different types of lines or different equivalent circuits for the line. These are different equivalent circuits for the line. See, any line of any length can be represented either in the RL lumped model or in the RLC lumped model or in the distributed model. Which model we have to select among these three? That is decided by what analysis you are carrying, what type of analysis you are carrying, and how better result made, how accurate you require in the result. That decides which type of model to be selected. So I think all of you getting my words? Yes. The RLCG distributed model is a universal model. RLCG distributed model is a universal model all the time. That's a better model to use for all cases of line analysis. Okay. Next thing. Somebody is having a doubt. I will try to clear it, whichever we have now. Let's take one more example here. Okay, I have right here long line. Let's take one more example here. Just listen. Look here, look here. We have a big power system network having number of buses. Let's say 100 buses. 100 bus system here. 100 bus system. So I want to carry load flow analysis on this. I want to carry load flow analysis on this. Yeah, look. 100 bus power system network. I want to carry load flow analysis. Load flow analysis means initial steps will be like this. Initial steps will be like this in the load flow analysis. See, the given system has to be converted into its electrical equivalent circuit. Then we have to go for the Y bus construction. Okay, given system has to be converted into its equivalent circuit. Then we have to go for the Y bus construction. Okay, one thing I want to tell you before moving into this, we said steady state analysis, transient analysis, right? Here, here. One of the best example for steady state analysis is a load flow. One of the best example for steady state analysis is load flow. One of the best example for transient is switching transient. Switching transient analysis. One of the best example for the transient analysis is switching transient analysis. Okay, let's move ahead. Let's move ahead. The next slide. See, obviously we are carrying steady state analysis now. Obviously we are carrying the steady state analysis. Okay, listen please, listen please. Let us say we have a line here. We have a line here of length 300 kilometers. We have a line of length 300 kilometers in that particular system. Number of lines, number of generators, number of transformers are there, but we are concentrating on one line that's of 300 kilometers. Okay, please listen this controversy. Listen this controversy, how we are going to resolve it. 300 kilometers length of line. Which model you suggest? 300 kilometers length of line. Which model you suggest? Tell me please. Distributed model, na? We will be suggesting the distributed model. Good. Next thing. Which analysis we are doing? Which analysis we are doing? Steady state. We are carrying the steady state analysis. See, while we are doing steady state analysis, already I said a restriction that the line should be kept in the lumped model. The line should be kept in the lumped model. See, as a length of line is more than 160 kilometers, according to the suggestions made by the people. According to the suggestions made by the people, we should keep that line in the distributed model. But analysis, what we are carrying is steady state analysis. According to the nature of this analysis, the line must be kept in the lumped model. The line must be kept in the lumped model. Getting this controversy? Following all of you. So the suggestion made by the people to go for distributed model, but analysis is asking me to represent the line in the lumped model. How to resolve this issue? How we can resolve this issue? See, we should not go for the RLC lumped model. We should not go for the RLC lumped model by sacrificing our accuracy. By sacrificing our accuracy. We should not miss our accuracy. We should not miss our accuracy. As well as we should not miss the steady state concept what we are saying. So for that purpose, listen please. First you represent the line. Listen please. First you represent the line in the distributed model like this. First you keep the line in the distributed model like this. For this model, you find out ABCD parameters. Find out the ABCD parameters. After getting those ABCD parameters, you construct a lumped model. Which will have same ABCD parameters. That lumped model we will use for this line representation. That lumped model we will use for this line representation. That we can call as generally equivalent lumped models representation of the long transmission lines. Okay, so I'm writing that statement. In steady state analysis, in steady state analysis. The distributed model of long line shall be converted into its equivalent lumped model. Equivalent lumped model shall be converted into its equivalent lumped model. In bracket, equivalent pi, or you can see equivalent t, equivalent pi or equivalent t, by using ABCD parameters. ABCD parameters of long transmission. ABCD parameters of long transmission line. Okay. Statistical analysis. The distributed model of long line shall be converted into its equivalent lumped model, equivalent pi or equivalent t, by using ABCD parameters of the long transmission. Okay. Next, let's see the equivalent circuits of remaining two models. Already distributed model we have seen this one as well as exact. So now let's think about the short line model, RLM, simple. Next, medium line. Okay, equivalent circuits for short and medium lines. First one, short line model. So it is a simple RLCV circuit we are saying. For total resistance and total inductance, we are going to keep it only one place. This is for the complete length of transmission line. Sending end side and receiving end side, you can say sending end side and receiving end side. And this is for the complete length of line. Next one, medium transmission line. Medium transmission line. So it's a RLC lumped model. See, actually, in the previous case, so-called short line, we have only two elements, RL series. Next case, we have to add that shunt capacitor. So adding that shunt capacitor at what place? Is it at receiving end side, sending end side, at any other place? That will decide the that will tell different models for medium line representation. First one, you can say total capacitance of line, shunt capacitance of line, we keep at receiving end side. We name it as receiving end capacitor model. Okay. So first one I am taking up receiving end capacitor model. So I'm keeping the total capacitance of transmission line. At the receiving end side. Right. So this is a sending end side. I'll say plus minus Vs. And it's a receiving end side. I can say it's plus minus VR. And this for total length of line. Receiving end capacitor model. Next one. Sending end capacitor model. Second one. Sending end capacitor model. So I'll keep like this, sending end capacitor model. Total RL we will keep like this. And the total capacitance we are going to keep at sending end side. Okay. And this is the sending end side voltage. And this is the receiving end side voltage. here. Sending end side voltage and receiving end side voltage. And again, this is for complete length of line L. For the complete length of line, sending end capacitor mode. Yeah. In the next model to be discussed here, I'll keep the total capacitance at midpoint of line. Means this RL I will divide into two parts, R by 2, L by 2, R by 2, L by 2. And the middle we keep the capacitor. That we can say midpoint capacitor mode or middle end capacitor mode. Middle end capacitor model. Middle end capacitor model. So I will be showing this R by 2, L by 2. R by 2, L by 2. And at the middle, I will be keeping that capacitor. Okay. So R by 2, L by 2. R by 2, L by 2. So this is plus minus, I can say it is Vs. And here it is plus minus, we can say it is VR. This is a charging current IC. And here also you can say charging currents in the sending end and receiving end capacitor. Middle end capacitor. And the next one I can say two-sided capacitor model. Double end capacitor model. So C by 2, C by 2. Double end capacitor model. Or you can say two-sided capacitor model. Okay, you draw this one quickly. Yeah. So fourth one, two-sided capacitor model. Total resistance and total inductance, I will keep it only one place. And half of the capacitor at the sending end side and remaining half at the receiving end side. And you say this is Vs sending end side, and you say it is VR receiving end side. And half of the charging current on one side and the remaining half on the other side approximately. Approximately half of the charging current one side, half of the charging current on the other side. Done. Next. See, this one, this middle end capacitor model can also be called as a T model, right? It looks to be a letter T, so it can be called as nominal T model. Nominal T model of line. And whereas the next one we are going to say as nominal pi model representation of line. Nominal pi model representation of nominal pi model representation of the line. Nominal T model, nominal pi model. Next thing. Yeah. So we'll take some small problems on this. Small problems. Before moving to that, one point I want to tell you here. We said 4 models here. That's okay. Receiving end capacitor model, sending end capacitor model, nominal T, nominal pi. Which model we should use for medium line analysis? Which model we should use for medium line analysis among these 4? If this question comes, what you have to answer is whichever the model acts as an equivalent an equivalent for the distributed model or exact model of line that we should use. I'll tell you like this. I'll tell you like this. We have taken exact model. First, we have done the analysis. We got some result. We have done the analysis. We got some result. And we have taken these four lumped models. For each and every one, we have done the analysis. We got some results. Whichever the lumped model result, matching with the distributed model result, that model we should use for analysis. In that perspective, this nominality and nominal pi will give the analysis results close to the exact model, so that we can use any one of these two models for the line analysis for medium lengths. Okay, so I am writing the statement. Kindly go through it. Nominal B is general. That's the meaning. General. Just by taking up that RLC from calculations, we are dumping into circuit. We are arranging. That's the meaning of nominal. Yeah, let me write. The nominal T and nominal pi model results will almost match with exact model result. Okay, will almost match the exact model result. So either nominal T or nominal pi can be used for medium line analysis. Okay, either nominal T or nominal pi can be used for the medium transmission line analysis. We don't use 1 and 2 models. Okay, again, in this nominal T and nominal pi, which model is preferable? Again, in between these two, nominal T and nominal pi, which model is preferable? I'll tell you. For example, in the similar way of previous discussion, we have one big system like this and we are doing load flow analysis. You say it's a 100-bus system. We are carrying load flow analysis. I have one line in this system of 150 kilometers length. I have a line in the system of 150 kilometers length. Kindly listen to me. For long transmission line, we have to use that equivalent pi or equivalent T. Listen please. 150 kilometers length. Okay, load flow analysis. First step is replacing these physical elements or replacing the single line diagram with the electrical equivalent circuit. Second step, going for Y-bus or Z-bus. Going for either Y-bus or Z-bus, anyone. Okay, listen. See, 150 kilometers means it will fall in the category of medium line. 150 kilometer means it will fall in the category of the medium line. And if you want to replace this medium line with its electrical equivalent, two options we are saying. One, we have to go with a T model. Next one, we have to go with the pi model. Following. See, let us say this node X, I am saying this node is Y. X and Y, two nodes. Same XY line represented with T. Like this. So this will come X and this will come Y. XY. Okay. And same XY line represented in pi. This is X, this is Y. XY. Tell me please. Is there any other node created here extra in the T model? Any node created extra in the T model? Yes, at the midpoint of line. At midpoint of the circuit, some extra node was created. So this is that extra node created or new node created. new node, or you can say extra node created here. But you see, in case of pi, these two are same. There is no difference. These two are same. There is no difference. Means, listen to me. If you represent transmission line in the T model, there is one extra node created at the midpoint. Because of that, overall number of nodes will increase in the system. If the number of nodes are increasing, definitely the size of the Y bus and Z bus will increase. And this analysis will become a bit laborious or more difficult. But if you go with the pi model, there is no increment in the number of nodes. Number of nodes will remains same. Size of the Y bus and Z bus is not going to be affected. I think all of you getting this point. Is it okay? Can I write? So I'll say T model representation of line. T model representation of line creates an extra node. Okay. So if lines are represented in T models, lines are represented in T models, the total number of nodes will increase. Total number of nodes will increase. Right? Total number of nodes will increase, and the size of Y bus and Z bus increases. That implies analysis will be difficult. So always line has to be represented in pi model. Always a line has to be represented in the pi model. Yeah. Okay. So next, let's take some small problems on this. Simple problem. Next slide. So let's look at this question. A 150 kilometers length of line. Has series and shunt reactances. As 50 ohms and 2000 ohms respectively. So if you want to check later, just to take one practical system and try to check how is the series reactance of line, series inductive reactance and shunt capacitive reactance. Already in the previous class, I have proven that shunt capacitive reactance will come very large in the order of kilo ohms. I have written here 2 kilo ohm. But series inductive reactance number is a bit less. That clarity we should have. Series inductive reactance is a low value. Shunt capacitive reactance is a very large value. Okay? Yeah. Since which of the following model model is used for line representation? Which of the following model is used for the line representation? Line representation in load flow analysis. Load flow analysis. Okay. Yeah. So I'm showing options here. Kindly go through it. First option. No resistance given in the data also. I'll give numbers. Yeah. So this is J 50 ohms minus J 2000 ohms minus J 2000 ohms, J 50, J 100, sir, 1000 ohms, J 1000 ohms, J 50 minus J 4000 ohms minus J 4000 ohms. This is J 50. Check that which option is correct. Pi model, only two nodes. There are no extra nodes, right? Pi model, whatever the physical nodes existing, that we have in the circuit also. There are no extra nodes in the pi. Yeah, you see, first of all, according to the problem what they have given, series inductive element we know naturally, series element is inductive in nature, shunt element is capacitive in nature. Series element inductive, shunt element capacitive. Okay. Series inductive reactance XL, that number is 50 ohms. Shunt capacitive reactance, we know it is 2000 ohms. Let's take a pi model first in a simple way. Pi model. Like this we have. So, half of the capacitance we keep at this place and remaining half of the capacitance at the other place. Inductance here. Yeah. Okay, listen please. See, this is XL. Series inductive reactance XL. JXL we should say impedance. Impedance means it is JXL. See, capacitive reactance or capacitive impedance will be minus J symbol. Capacitive impedance will be minus J symbol. This is a point where you have to be clear. So it's minus J XC1, and this number is minus J XC2. Minus J XC1 sending end side, minus J XC2 receiving end side. See, we have to prefer to go for pi model. That's why I have drawn directly, because we said load flow in the question. So we have to go with the pi model. So I have drawn it directly. Okay, what about the XC1 and XC2 values here? XC1 and XC2 are equal. XC1, XC2 are equal to what? 1 by omega C by 2. XC1, XC2 values are equal to what? 1 by omega C by 2. This is nothing but 2 by omega C. 2 by omega C, which is 2 times of XC number. So on the sending end side, we should keep double the value of shunt reactance. Receiving end side, you should keep again double the value of the shunt reactance. So this number will come to be minus J 4000 ohms. And this number is again minus J 4000 ohms. Like this we can say. And at middle, of course, it will be J 50 ohms. J 50 ohms. Okay. So which option is correct now? Which option is suitable one here? That is option C is a suitable one. J 50 minus J 4000 minus J 4000. So correct answer from the options will be C. Correct one will be C. Minus J, that is just for a capacitor. Capacitive impedance is minus J. Capacitive impedance will come to be minus J. Yeah. Yeah. Next. So for example, same problem I'll copy. With a small change, just you have to give the answer for it. Same problem I am copying now. Rather than 150, I am keeping this one only 50. That's it. Only one change I made. 50. Please give me the answers for this. 50 kilometer length of line has series and shunt reactances, 50 ohms and 2000 ohms respectively. Which of the following model is used for the line representation in the load flow study? What's your option? What's your option? See, again, you have to go with C. Again, you have to go with C. Why you are changing your answer to D? Again, in this case also, your answer will be C only. Answer will be C only. Why? Why we have to take the answer again as C? Only one rule is that if the shunt element is given, we should not neglect it. If the shunt element is given, we should not neglect that. Okay, we should take into the circuit irrespective of length of line. Irrespective of the length of line, if the shunt element is given, that we should not neglect, we should take into the circuit. By taking that into the circuit, we should take the option as C only, irrespective of length of line. Okay, right. So next, let's say one more small question. IES question it is. Next question I am saying IES question. Which of the following length of line is quite suitable to represent in equivalent pi model? Equivalent pi model. Of the following length of line is quite suitable to represent in equivalent pi model. See this option A, 50 kilometers. B, 150. C, 250. D, all the above. Please kindly remove this option D. Please kindly remove the option D from your mind. Check whether it is A, B, C. That's it. Why it is not D? Why the D option is not suitable means he said here quite suitable to represent the line in the equivalent pi model. Okay, which length of line among these three is quite suitable to take up in the equivalent pi? Tell me please. See, actually, you know, which model he said? Equivalent pi. Which model he said? Equivalent pi. Equivalent pi model is for which line? Equivalent pi model is for which line? Short line or long line? Long line. Long line will have equivalent pi, equivalent t. Okay. Medium line will have nominal t, nominal p. Long line will have equivalent pi, equivalent t. And then medium line has nominal pi, nominal t. Nominal pi, nominal. Okay. So as he is saying about equivalent pi model, we have to choose our answer as long length of line. So it will be 250 kilometers what we have to select. Then what's the difference between these things? Nominal T and nominal pi, as well as equivalent pi, equivalent T. Construction wise, we have a difference. Construction wise, we have a difference. Okay. See, particularly already I discussed in today's class itself, how you are constructing that equivalent pi and equivalent T. How you are constructing that equivalent pi and equivalent T? The distributed model of long line, we are taking into ABCD parameters first. These ABCD parameters, by using these ABCD parameters, we are constructing that equivalent pi and equivalent T. So these are the lumped models. Lumped models constructed by using ABCD parameters of distributed model. ABCD of the distributed model. You should calculate ABCD of distributed model. From that, we should construct the lumped model that you can say equivalent pi and equivalent. Clear? Next, how you construct nominal T, nominal pi? These are also lumped models only. That's okay. How you are constructing them means by the direct placement of RLC in the circuit. Means for the transmission line, we'll calculate RLC parameters that will keep into the circuit. That's it. So these are lumped models. Lumped models constructed by the direct placement. By the direct placement of RLC in the circuit. Of the RLC in the circuit. Okay. So these are difference what you have to observe between the nominal models and the equivalent models. So now we will stop at this point our lecture. Tomorrow we will be starting with ABCD parameters. ABCD parameters calculation will be starting. Okay, so I will make all the hands low. If anybody have doubts, you can raise your hands. Ramakrishna.
Hello, good morning, sir.
Good morning, Ramakrishna. Tell me.
If it is given like this, a 50-kilometer length of line and distributed model in steady state, then which line we should take, sir?
50 kilometers length of line, distributed model means you should go for equivalent pi or equivalent T.
A short line, long line, or medium line in that case.
50 kilometers length of line, distributed means long line.
In steady state too also. Okay, sir.
Steady state also. That's a model.
Okay. That's
okay. Salman Khan.
Good morning, sir.
Good morning. Tell me, Salman Khan.
Sir, we have seen the formula for voltage regulation as a no load voltage minus full load voltage.
That is okay. Actually, the exact definition is this. How much rise in the voltage you are going to get after disconnecting the load?
Okay.
That's the original definition of the voltage regulation. Not the definition like no load minus full load by full load.
Yeah, means from this formula we are getting like
that is the extension for this. Okay,
yeah,
but that is not the original one. You should not say that the change in the voltage from no load to full load.
Okay.
As a definition, if you are writing, we should not write in that manner. We should say the rise in the voltage when the load is suddenly thrown off.
Okay, sir.
Then ultimately the equation may come like no load voltage magnitude minus full load voltage magnitude by full load voltage magnitude.
Yeah, right, sir. Sir, other formula also I have seen somewhere. No load minus
is used for transformers for some special purpose.
Okay. For transformer that is.
Transformers.
And sir, another doubt is that if you use means a lump model and distributed model, answer will be same, na sir?
Almost it will come same.
Almost same.
Almost same.
Means for long.
For example, I'll tell you, for 50 kilometers length of line, even though you do analysis by lumped model or distributed model, a result may not vary a grade.
Right.
Okay. But if you have a line of 300 kilometers length,
okay,
you are using medium line model for that.
Medium line model.
Means RLC lumped model, maybe nominal T, nominal pi you are using. And you are using long line model. then there is a difference.
Sir, if I consider all the parameters in lumped models, then also it will be different.
That's what I am saying to Salman. If the length of line is getting increased, then there is a great deviation between lumped analysis and distributed analysis.
Yeah, because from the diagram, I visualize that all the same 1 ohm are just placed at different places. Then
doing analysis on that is not at all possible, right?
Right.
Ultimately, you have to convert that model into equations. Using those equations, you should find out ABCD that we should use in the analysis of line. That's what I said. Exactly distributed model means there is no network representation. It will be represented only as mathematical equations.
Okay, sir.
So it is approximate model just to get a feel about it. That's it.
Right, sir.
We don't use it anywhere in the analysis also.
Okay, sir.
Okay.
Thank you, sir.
Yeah. Bala Vinkesh.
Sir,
tell me.
Sir, for 50-kilometer line, if we need to do the transient analysis, means we need to go for distributed model or lumped model.
Distributed model.
If it is steady state, means lumped model, sir.
Lumped model you can use.
Sir, at the same time, when we need to use the nominal pi and nominal t, sir, in steady state or transient?
For length in between 80 to 160.
Yes, sir.
Steady state analysis.
For transient, we should not use nominal pi and nominal t.
No.
Okay, sir.
Transient, if you say, it's a distributed.
Okay, sir.
Okay.
Yeah. That's it. Thank you, sir.
Vishwanath.
Hello, am I audible, sir?
Yeah. Tell me, Vishwanath.
Sir, actually, you said that the charging current is directly proportional to V into F into capacitance per kilometer into length.
Okay.
Sir, how is that? Can you explain once again, sir?
We discussed in previous chapter, no? Charging current formula.
Yeah, okay. Only that's
from that it came.
Okay, sir.
Okay.
Sir, and in voltage regulation, you said that the VR naught minus VR by VR. Sir, if the VR naught is taken at the transient time, right? No, sir.
No, it's not in transient time. It's in steady state only.
Sir, at the time of the switching, the VR naught is taken.
No, not switching exactly.
Okay.
It has to be disconnected and it has to settle down.
How is the VR naught is greater than VR, sir? If the load is
may or may not be. We don't know, Vishwanath.
It may be negative.
Maybe we don't know. That we have to investigate and we have to tell. Voltage regulation value may be negative, may be positive. Both possibilities we have, right?
Yeah, sir.
So I didn't say anywhere VR0 is more than VR.
Okay, sir.
According to the definition, it is rise. Rise may be negative also, right?
Yeah. That's it, sir.
Yeah.
Thank you, sir.
Yeah. Yashwant.
Sir, am I audible?
Tell me, Yashwant.
Sir, previously you've taken a 150-kilometer line in 100 bus system. And you told we use pi model here because we don't want extra nodes. Sir, in a 100 bus system, each bus can be noted as a one node, no, sir?
One node, yes.
So why not use 100 T models in a cascade, like in a distributed system?
T models in a cascade. What's the purpose of that?
So that we can cover each node. Each node in the T model can be given for one.
But you are losing your main
bus.
node, right?
Okay.
You are losing your main bus.
Previously in pi model we have no main bus. No, main
bus
node
is
no.
there XY.
Sir.
So in the pi model we have that XY, right? What you are saying is I will be connecting number of T lines in cascade so that I will add this series impedance to the next line series impedance.
Sir. So that we can consider all the 100 buses.
Then you will be losing this Y and X and Y, right?
Okay. So in T model we will be losing our X and Y, sir.
If you are doing that method, what you said.
Sir.
But I was not interested to lose it. So I have to keep this T model as it is in the circuit. And I have to find X node voltage, Y node voltage.
Sir.
then obviously number of nodes is increased by this new node.
Okay, got your point. Okay.
Okay.
Okay, sir.
Yeah. Vishwanath. Parre Vishwanath.
Hello.
Tell me, Vishwanath.
Sir, I have doubt in calculating the GMD of the system.
Okay.
Suppose if we take the three conductors which are at a distance D and 2D, how will we calculate the GMD, sir? I take cube root of GMD of A into GMD of D into GMD of C.
Okay, that's also correct.
But the answer will be wrong, sir. Ante, I get the different answer.
How many conductors you are taking? Three or
three
two?
conductors, sir.
Three. Okay, this is A.
B.
So it is B and this is C. Okay.
Yes, sir.
Tell me, please.
Between
Distance
A and B.
Between A and B?
D.
Okay. B and C?
D. 2D.
2D.
Yes, sir.
Okay. What do you want first?
GMD of system with GMD of A, GMD of B.
What is GMD of A?
Root of D into 3D. Yes, sir.
GMD of B?
GMD of B equal to D into 2D.
Under root.
Yes, sir.
GMD of C?
3D into D. Root of
3D into D.
yes,
under
sir.
root. What is GMD of system?
Cube root of GMD of A, GMD of B, GMD of C.
What you get now?
1.61 into D, sir.
Just play it. This one. B into 2D. Root of 2D. So it will come like cube root of D into 2D into 3D.
Yes, sir.
Then you get cube root of 6 into D. Getting?
Yes, sir.
That's it. That's the correct one.
Yes, sir. Sir, I had made a calculation mistake.
Okay.
Thank you, sir.
Bhaskar.
Hello, sir.
Tell me, Bhaskar.
Sir, voltage regulation means not the voltage drop between sending end and receiving end.
It's not exact. I can say it is approximately, but it's not exact voltage drop.
Okay. How you are saying this transient analysis is done by distributed, sir?
See, while you are doing transient study, you need to trace up the voltage value at each and every point on the line.
Okay.
There is a rise in the voltage or fall in the voltage, whatever it is. So we have to track the voltage at all the places along the line.
Okay.
For that purpose, you have to go with the distributed mode only.
And for any type of length, we are doing long line model, sir. Means
any type of line. For any line you want to do
in
transient analysis means obviously you have to trace up the voltage at all places, right?
Okay, sir. Okay, sir.
That's it. Any other doubt here, Bhaskar?
No, sir.
Yeah. Jessica.
Hello,
Jessica.
sir.
Tell me.
Sir, I did not get the physical meaning of this line charging current, sir. What does it actually mean?
Because of electric flux linkages, we will have an exchange of current from one conductor to other conductor.
Exchange of current. How, sir? Like,
see, if you have two conductors here, this is a conductor A operating at certain voltage, and this is a conductor B operating at some other voltage.
Okay, sir.
Okay. Say this. Now, what I'll say is, this is operating at some voltage VA you call, and this is at VB.
Okay, sir.
And it will be acting as a line charge. Okay.
Yes.
Because of this charge in the sense, it will be leaving the electric flux lines.
Yes, sir.
Radially outward, you can say. So these are the electric flux lines, what it is leaving out radially outward.
Yes, sir.
And these electric flux lines will terminate on this conductor B. Electric flux lines terminates on the conductor B. Okay.
Okay, sir.
And assuming that this is a AC conductor, so obviously this voltage VA is a time varying signal.
Yes, sir.
This Q is also a time varying signal.
Okay.
then obviously this electric flux is also a time varying signal.
Okay, sir.
The time varying electric flux attacks on the conductor B. So the conductor B is going to experience rate of change of electric flux linkage.
Yes, sir.
Conductor B experiences a rate of change of electric flux linkage. What do you mean by that rate of change of electric flux linkage? What do you mean by rate of change of electric flux linkage? Current. Where it is created, that current. Who is experiencing that current?
Conductor B.
Conductor B is experiencing that current. Because of what?
This
Conductor A
electric.
flux. Because of the conductor A electric flux, there is a current induced in the conductor B.
Okay.
That we should show in our circuit,
So
right?
Sir.
That's the charging current.
Okay, okay, sir.
Okay.
Sir, and yes, I got it, sir. And I did not get the difference between nominal and equivalent. What
Already I have written it. Just read number of times this one. You will get clarity. What I have written equivalent?
Lumped model
Constructed by using ABCD of the distributed model. Which is the original model? Distributed. Okay. The distributed model, for the distributed model, first we find ABCD.
Sir.
By using that ABCD, we construct a lumped model.
Okay, sir.
That you call as equivalent by equivalent.
Okay, sir.
What is nominal model?
Lumped model which is constructed by directly placed.
Directly, or else I am keeping in the circuit, we are constructing a pi model or T model. That is nominal.
Okay.
Getting?
Yes, sir. Sir, and you told that static regulation is called as voltage regulation.
That's also I said, I think, here. Because of the load variation, current is going to change.
Yes, sir.
Okay. But how is the voltage?
Almost constant.
Even though you say almost same, there is a change in the voltage, right?
Sir.
The change in the voltage is given by the term voltage regulation.
Okay.
Hence, it is named as voltage regulation. Static regulation, hence it is named as voltage regulation.
Okay, sir. Sir, okay. And one last doubt. Sir, in that like when we are using T model, we are creating new nodes, you told us, sir. But in pi, we are not. So, like you told that there is an increase in the
number of nodes will be remain same in the pi model.
Yes, sir. Sir, but you told that there's an increase in the size of bus. Why it's
increasing size of Y bus. Attended analysis?
No, sir.
Okay. See, generally the size of the Y bus and Z bus will be number of buses by number of buses.
Okay.
Okay. So if you have a 100 bus system, Y bus size expected will be 100 by 100.
Okay, sir.
But if you keep that in a T model, there is an extra node created.
Okay, sir. So this
number of nodes will increase,
100 means what is that numerator and denominator? I know, sir.
What is it?
Like you told 100 by 100. So
1 minute. Matrix size I am saying, not denominator and numerator.
Okay.
Matrix size. Okay, so that 100 will be number of buses. Matrix size will be 100 rows and 100 columns.
Okay, sir.
But if the T model, if you are using, number of nodes are increasing.
Sir.
Obviously, number of rows and columns in the Y bus will increase.
Okay, sir.
And analysis will be a bit difficult.
Okay, sir.
Yes.
Thank you, sir. That's it.
Haripriya.
Good morning, sir.
Good morning, Haripriya. Tell me.
Sir, in voltage regulation, why voltage magnitude increases? Rises?
I didn't say it's going to be increased.
Means why it changes, sir?
1 minute, please. GMDC. is, I am sorry, it is 3D into 2D GMDC. 3D. Tell me, what's your doubt? I didn't say it's going to be increased. That's the definition. What we are saying is rise in the voltage.
Why it
Rise
rises?
can also be negative also, right?
Why it changes, sir?
Why it changes means whenever you disturb the load, definitely the voltage drop in the line is going to be affected, right?
Okay.
Because of that effect, definitely receiving end voltage changes. Okay?
That's all.
Yeah. Any more doubts? Please raise your hands quickly. Same.
Good morning, sir.
Sir,
doubt is in the distributed system that we are at for transient analysis, distributed model is used.
What is that? Please
Hello.
repeat again.
In a distributed model, in a transient analysis, we are using distributed model.
Yes.
Okay. When there is but in some problems, I have seen that the circuit breaker is connected across the capacitor, and that transient, that is active recovery voltage, or that all are calculated on the basis of only LC oscillations or RLC circuit. Simply
RLC
means
circuit.
RLC circuit. But when we go for long transmission line, then that will be distributed.
That's the approximation they will do.
Means how we then calculate actually. There is not directly L and C element is there. This is
No, that they will do as an approximation. If you are using distributed model there, that will become even more laborious to do analysis.
Okay. Then approximate means we have a equivalent pi or equivalent T.
Lump.
Then here written it is distributed model has to be used in a transient analysis.
That is a force what we are making. We are forcing the people to use distributed model for transient analysis.
But in actual practice, it is lump.
Actual practice means if they are feeling it is more difficult to use because capacitor, that circuit breaker switching, capacitor switching, all these things are there.
Yes.
Yes or no? If you take that line as a long line again, then the whole analysis will become more laborious.
Okay.
But condition they might have converted and they have done.
In a programming, how we are using it?
In programming long transmission lines, they will go with the EMTP programming.
Okay.
Electromagnetic transient programming, they will use EMTP.
Okay, means it will be accurate result.
EMTP will be accurate. Yes.
Okay.
So to get an accurate result, what I am suggesting is you go with the transient model.
Okay.
If you are not, that's your wish then.
Means for only get problems, we are we seeing that a small element.
Yes. For example, you see Swain fault analysis.
Yes.
To calculate transient or subtransient current, we are using lumped model, right?
Yes.
Not distributed.
Okay.
But what purpose? Only to find out current in that span of time.
For that span of time.
For that span of time to find out subtransient current, we are using lumped model.
Because subtransient is unstable, means it will be maybe
current will change, no, in that span you got the current. Again, if the span gets changed, we have to modify the circuit.
Sir, if you means for that short interval, we are actually using in a real practice also we are using lumped model.
Lumped model, yes.
But exact will be given. Exact
strictly,
result will
strictly the suggestion is you have to go with the distributed.
Okay. Thank you, sir.
Okay. Pavan. Pavan. Pavan, are you there, Pavan? Do you have any doubt? I'm unable to listen to you, Pavan. So raise your hand, please. Anybody have a doubt? Gangadhar.
Sir,
Tell me, Gangadhar.
in one case, one boy asked no, sir, to find GMD of 3 conductors last
Okay.
class. Sir, is it for a transposed or untransposed, sir?
The untransposed case, you use these 3.
Yes, sir.
Transposed case.
Directly distance between those conductors, no, sir.
Transposed case, you use this one.
Okay, sir.
Okay.
But this is also okay, sir. I got it, sir. Okay, sir.
Karthik.
Good morning, sir.
Good morning, Karthik. Tell me.
Sir, I have a doubt in one question, sir. Calculation of loop inductance of the system.
Okay.
Sir, I will tell the question, sir. A single phase composite conductor system has the conductor configuration as shown in below. Radius of the conductors in forward path is 1, 2, 3 is 4 centimeter. And radius of the conductors in return path 4, 5 in 4.9 centimeter. Spacing between conductors is given in figure. Loop inductance of the system.
4.49, second one, right?
So 4.9.
I think this distance is 1 meter.
Yes.
1 to 2.
Yes, sir. 1
2 to
meter.
3 also 1 meter.
Yes, sir.
1 to 1 dash 2 meters.
Yes, sir.
2 to 2 dash also 2 meters.
Yes, sir.
This gap is 1 meter.
Yes, sir. 1 meter.
Okay. So you consider this as a forward path phase A.
Okay.
You consider this as the return path phase B.
Okay, sir.
Forget about loop inductance for time being. Loop inductance is simply LA plus LB. That's the answer what you have to give.
Okay, sir.
What is LA formula?
0. GMD.
GMDA by GMRA.
Yes.
What is GMDA?
GMDM.
GMDA means you have to take the geometric mean of distances from phase A to phase B.
Yes, sir.
What are the distances? 1, 1 dash, 1, 2 dash, 2, 1, 2, 2 dash, 3, 1, 3, 2 dash.
Okay, sir.
Total 6 mutual distances you get.
Okay, sir.
Geometric mean of the 6 distances will be GMD of A.
Okay, sir.
GMRA means you should take only 1, 2, 3.
Okay, sir.
And you know how to do it. Similar to bundle.
Yes, sir.
Okay.
Okay, sir.
Dump the values, you will get LA.
Okay, sir.
And what's the LB formula? Point to LN of
to LN of
GMDB by GMRB.
GMDB. Yes.
What is GMDB? Geometric mean of distances from B to A.
Yes, sir.
1 dash 1, 1 dash
Okay,
2,
sir.
1
Okay,
dash
sir.
3. Next, 2 dash 1, 2 dash 2, 2 dash 3.
Okay, sir.
Geometric mean will give GMD of B.
Okay, sir.
Then GMRB, it will be similar to what we call bundle count.
Okay, sir.
So don't bother about this solution. You do LA, LB separately. Add them.
Okay,
That is your answer.
Okay, sir.
He is asking loop inductance. Okay?
Okay, sir.
Yeah. So any other doubt you have, Karthik?
No, sir. No, sir. Thanks.
Any more doubts? You can raise your hands. Else we'll close. Okay. So I think nobody's having a doubt. Thank you.